Hello students, so this is Brock Skaggs. So I'm going to make this video showing how to run a analysis of a rod that's in pure torsion in SolidWorks Simulation. And so you can see the rod we're going to look at in this example. We've got a square cross section extruded at some length L, and the specifics are down here. That the overall length is going to be 36 inches, and then you'll notice there's an L2 area there where we've kind of have the gray hashing, and that's basically where these torques are going to be applied. And so if you're thinking back to the 424 lab course, on one side you kind of have this vice grip that holds one end of the rod stationary, and the other end you have this kind of movable vice grip that's attached to a pulley that causes this rotation to happen. And so think of those gray areas as where those vice grips are clamping onto the rod itself there. I don't know if it's exactly 1 inch there, but we can adjust that value if needed to make it closer to the actual lab apparatus there. The example I'm using is a square cross section with a side length of 1 inch. The applied torque you can see is 500 inch-pounds. And the material, I'm just going to say it's 661 T6, which has a shear modulus there of 3.75 times 10 to the 6 psi. As far as where I'm getting the equations and the material properties, such as that shear modulus for the aluminum alloy there, is from the textbook we're currently using for the 423 class. And so you can see the applied strength of materials citation there. And so this is specifically in chapter 4 of that book, where you'll see how to calculate the torsional shear stress and the angle of twist for this non-circular cross section. And so what I've already done is went through and done the theoretical side of the calculations here, so we can know if we're getting right answers out of SolidWorks here. And so we're expecting to see that the maximum torsional shear stress experienced by this member to be roughly 2,404 psi. Also, the angle of twist we're expecting along the length of this member that's free to rotate is roughly 1.90 degrees there, so quite a small number there in radians. Also, just to make a note why this number here is 35 and not 36. Well, do remember that this part here on the backhand side is going to be clamped down. It's not going to be able to rotate, and so we're taking L1 minus 1 L2 value to get the free length of the rod here that's going to be allowed to rotate there. There was the slight modification that you need to be aware of. And so with that much done, we can go ahead and hop into SolidWorks now and start the analysis there. And so you can see I'm just starting a usual part template, checking units. IPS is great. And one thing I'm going to do, you've got the three planes here, the front, top, and right. I'm going to be sure to make my first cross-section sketch on the right plane here. And I'm going to be extruding it in the positive X direction. Now, the reason I'm doing this is because depending on which way the rod is oriented here, it's going to depend on what shear stress plot you need to look at in SolidWorks Simulation. And so here I'll be sure to get the sketch on the right plane. And it's going to be a very simple sketch here. Just a square with a 1-inch side length. So just like that, we've got a nice fully defined sketch. I've centered it about the origin, and then I will go ahead and extrude it out, and I'm going to extrude out the entire length there. And so that was, I believe, 36 inches was the overall length. Going back again to this diagram. Next, I've got to make these kind of grayed regions here, or at least make it so I can select those inside of the simulation portion of SolidWorks. The way I'm going to do that is I'm going to use the split line tool. But before I get to split line, what I'm going to do is I'm going to get back on that front plane here and go normal 2, and I'm going to make some sketches. And so these sketches right now are just going to be vertical lines, and each one is going to be 1 inch from the extreme edge there. And so there's the first one off on the left side, and then a second one here on the right side. And these will be used for my split line tool. And so coming back to an ISO there, I've got those line segments drawn out, 1 inch from the extreme ends of the rod. And so what I can do now is I'll just exit the sketch. Notice sketch 2 is still selected, and so I can go straight into split line under the curves drop down here of the features tab. And it immediately picked up that sketch 2 since I already had it selected. Projection is the type of split that I want to do. And so what I want to do at this point is just select the faces I want to split. And those faces are going to be all 4 of these faces, those longer faces associated with this rod. And so notice right now, no matter where I selected on those faces, it selected the entire face there. But that's going to change as soon as I make the split line. And so now after the split line, you can see these edges happening on these faces. And so now I have a distinct face here, which is different from that face there and different from that face here. Same thing on the other 3 sides as well. And so what this allows me to do in the simulation portion is apply the fixture or apply the torque just to these faces and have these faces be unloaded. And so it seems like a good place to be sure that I have it saved. I'll just name this Torsion Rod. And so that should complete most of the modeling. There's only one more thing we want to do, and we want to put in an axis. And so I'll go ahead and show the planes back. So one way to apply a torque inside of SolidWorks Simulation is to use a cylindrical face in order to get that axis that the torque's trying to rotate about. But here we obviously don't have a cylindrical face, and so we'll do it a little bit different when we'll put the axis in here. This axis will also help us when we go to calculate the angle of twist as well. And so what I'm going to do is just select the front and top planes, as you can see, and create an axis at their intersection. And since I centered that very first sketch I made of the cross-section at the origin, that axis should run right through the middle of this rod, which is exactly what I'm wanting. At this point we can go ahead and hide the planes, but I'll just keep the axis here. And so far so good. Now we can go to the Simulation tab and go to New Study. I'll just leave it as Static 1, and I do want a static type of study. As far as walking down the tree structure here, the first thing I'll do is I'll tell it the material. We said it was a 6061 T6 specimen, so go right click, apply material. It's under the aluminum alloys, and we should have 6061 T6 there. So I'll apply that to it. Don't really need connections here, but I need to go into Fixtures now. And so Fixtures, I'll just click on the Fixed Geometry from the right-click context menu there. And I'll use Fixed Geometry to approximate the side of the rod where it's being clamped into this fixed vise here. And so here I'm going to say, well, my vise is going to clamp into all 4 of these sides and hold that in place just like that. Where I think similar to the lab, this face here is free and doesn't have anything clamping on it. Next I'll go to the opposite end here where we've got these faces here that we created with the split line, and we'll apply a torque to them. So here I'm going to go to External Loads, right click, and go Torque. Here torque's pre-selected for me, and then the blue box is waiting for me to select faces to apply the torque, and so I'll select these 4 faces, very similarly to the way I did the fixture on the other end. And so notice now they're kind of pointing up, which is not really what I want. And so here I'm going to hop into this next box, and if I hover over it for the tooltip, it says Axis, Cylindrical Face for Direction. And so here it's wanting us to help it figure out what's the axis that this torque's trying to work about. And so that was the whole point of putting this reference geometry axis, axis 1, in here. And so I can then select axis 1, and you can see the arrows now look like it's trying to rotate it in the counterclockwise direction if you were looking down the x-axis toward the origin. And so we'll go to English. The value we wanted, going back to the notes here, were 500 inch-pounds. And so 500 inch-pounds here. The one thing to be careful of, since we did make multiple selections here on the faces, we have 2 different options. Is each face a different 500 pounds or the sum of all of those 500 inch-pounds? And so in this case we don't want 500 inch-pounds per item, we want 500 inch-pounds total there. Just be careful on that, because obviously that can get you vastly different results depending on which way you interpret the face selection as well as the input box here. But 500 inch-pounds total is correct for this example. And so looking at this, I think we're ready to go. And so I'll just go ahead and create mesh. I'll just pull it a touch over here to the fine side, so I can have a little bit smaller element size. You can see the elements there. And then I'll run the study. It's a fairly simple model, so you could hear SolidWorks chime when it's done there. It runs very quickly, and you get this very distorted shape looking at it right now. And so it went to the default stress plot, which is the von Mises plot. You can see the units are in pascals up here. The deformation scale is almost 221 there. And so we needed to make some adjustments here. And so the adjustment I'm going to make is I'll right click and I'll edit the definition of the stress plot. First thing, I don't want to look at the von Mises stress. I want to look at a shear stress plot. And so I've got actually 3 different shear stress plots to look at here. The tau xy, tau xz, and tau yz plots here. And this is where you have to be careful depending on which way you've extruded the member as far as the orientation of it. So you need to be able to select the right plot accordingly, and also select the right spot on the plot since we have a square cross section. And so for this one, if you're following along exactly, I will want the tau xy, which is the shear stress in the y direction there. I'll just leave the units as psi here, and deformation scale I'm going to go down to true scale, and on chart options I'm going to go ahead and go to a floating, I'll just say with 2 decimal places here, and I'll accept that. And so you can see a lot different here. Probably the most noticeable thing is that the deformation scale, you have a much more realistic look of the model itself. And so here you can see the red side and the most positive numbers are very close to the blue side and most negative numbers here, which I would expect. And so we'll just investigate the positive side of it here. And for this specific example of a square cross section, the max shear stress should be located right at the middle of each of those side points. That's something that you'll find if you look in the Mott textbook there. And so I've got this axis here running right through the middle, so I'll just select very close to that axis there. And the value shouldn't change a whole lot as I move along the length of the member, so I'll just pick near the middle. And you can see I've got 2,388.16 psi there, and kind of reverting back to our hand calc, so it's 2,404, which is fairly good in terms of percent error here. I'm getting roughly 0.7% error there. So a very good agreement between the theoretical side as well as SolidWorks Simulation here as far as what it's spitting out for that shear stress value due to this torsional loading. And so that's kind of half of our problem, right? Figuring out the max torsional shear stress, and we have verified that. The other part was the deformations. How much is this thing going to actually twist as this torque is applied? And so to do that, we're going to go down into the displacement plot. And again, you've got this grossly exaggerated view to begin with here. And so what I'm going to do is I'm going to right click and edit the definition, very similar workflow to the shear stress plot. And here I'm going to go ahead and just leave it at UX, but one thing I'm going to do is I'm going to come down here in advanced options and I'm going to select a axis. And so that's going to be the same axis 1 here for reference geometry. And all of a sudden you'll see things change a little bit here. Just to show that change, notice the axis is not selected, and UX, UI, and UZ are just the X, Y, and Z displacements in this coordinate system. Well, if I select the axis, now all of a sudden X, Y, and Z, UX, UI, and UZ become radial, tangential, and axial displacements there. The others have changed a little bit, I believe, as well. And so that's just something to look out for. And so here we're interested in this tangential displacement. And since we're doing everything in inches, let's keep the length unit consistent as inches there. And again, I'm going to go to true scale. And I'll just accept that plot there. And so you can see the plot just makes sense a little bit. Here you're not going to see very much displacement at all when we get very close to the fixed connection here. That's why it's trending to 0 here. And then on the far right end and the far extreme corners of the rectangle is where this thing's going through the most tangential displacement there. There's these points on the very edges or the very vertices of the square cross section are basically trying to rotate there. And so this number here is what we'd want to take for our bit of hand calculation here. And you can see the value 2.302 times 10 to the negative 2. And so let's go ahead and get back into OneNote here. Make the note here that was 2.302 times 10 to the negative 2. Here we go. Oops. This is 2.302 times 10 to the negative 2 inches there. Just double checking the SolidWorks value. And so here we're going to do something in terms of this small angle approximation. I've got a hyperlink here if you just want to Google it and follow the Wikipedia page. It's probably the easiest way to do it. And so the idea here is this: if this angle theta is small enough, we can make this approximation here that theta is going to be about equal to the tangent of theta. And so the image here that I'm trying to show is that the black is the original orientation of that square cross section. Basically think if you were looking down the x-axis here, and so the black would be this original square cross section that has not been rotated, and then the gray, you can think of that being at the free end here, where it's gone through this rotation here. And so we've got this point here, the very top left vertex of the square is basically going to rotate to this position here. There is going to be some arc length that it's going to rotate through here, but if that arc length is small enough, we can approximate it by a straight line there. Similarly here, we can figure out this D1 value, just because we know the side lengths of the square cross section. It's basically half of a diagonal there, and so I've already made that calculation. The DT is this other length, and this theta would be approximately dt over d1 using this small angle approximation. Again, the smaller that angle, the better that approximation is going to be. If this angle starts getting bigger, trending away from 0 in radians, then you're going to have more and more error there. And so this one, I believe, is going to end up being okay since it is a pretty small displacement. And so here we'll just throw these numbers in here to run the calculation. And so we've got 2.302 times 10 to the negative 2 inches here, divided by 0.707 inches here. And I'll get out my calculator and run that through real quick. 2.302 times 10 to the negative second divided by 0.707. That's roughly 0.032. I'll just say 0.033. We'll just leave it 2 decimal places there. Get my eraser out here. And back to the pen. 0.033. Units on this is going to be in radians here. And so if we make the usual conversion there, I can multiply this guy by 180 degrees divided by pi to get it to degrees. That's roughly 1.87 degrees there is what we're getting from that bit of SolidWorks. And so looking at the theoretical value here, we were expecting it to be about 1.90. Here we're getting 1.87. So again, we're getting very good agreement between SolidWorks and our theoretical calculations in terms of both the maximum shear stress that this rod's going to experience, which is what we did first, and then also the angle of twist, with a little bit of a calculation that you had to do after just reading the result value from SolidWorks. And so I think that is enough for this video. Thank you for watching the video, and hopefully this helps you explore torsional loadings inside of SolidWorks Simulation.